Hi, it's time for another math easy solution. Time to discuss further into differential equations and now look at further at the other models of population growth as opposed to the basic logistic and exponential equations. And I'm going to go over part 2 of the example 1 video I went over in my last video, which was on the modification of the logistic equation, which included this negative 15 value in this logistic equation that we've been using for many videos prior to. And this one, like I showed in that video, it was a harvesting constant. In other words, in the example we looked at was a fish population, and this was the constant rate of fishing. And basically I solved in the last video A, B, C, and D, and now we'll solve part C, which states to solve this differential equation explicitly, either by using partial fractions or with a computer algebra system. I'll just use partial fractions. You could just go Google for computer algebra system calculator to do that, but I'll just do partial fractions in this video. And then use the initial populations 200 and 300 to get the equations for these two different populations, and then graph the solutions and compare with sketches in part D, where we used the direction field to solve those solutions graphically. So make sure to watch the previous video to get a better idea of it, and then in this one I'll just go over part E. So recap on that previous example. So again, that negative 15 represents harvesting a fish. In other words, it's the rate at which fish are caught. So you include that in that growth rate formula, or the growth rate of the logistic formula. So this dp over dt is growth rate, so we're just minusing the fishing rate. And then this is how the solutions looked like. We had equilibrium solutions at 250 and 750, which is a flat line. And then when you had it below 250, it goes something like this. And then the other one is going to go up like this for 300. And in part E, we're going to look at initial populations 200 and 300, in which we expect that graph, the solution should go up like this and then level off at 750. But if it was at 200, this would go to 0. In other words, that's overfishing. So from the graph above, again I solved those 250, 750, and then so that's just part D. These are all from the previous video, so make sure to watch that. So let's look at part E. So we want to solve it explicitly, so what we'll do is write the differential equation, but I don't want to reinvent the wheel, and what I'm going to do is, this was the differential equation. I simplified it in my part C video, and then I got to this point right here. And instead of 0, I'll just write that as dp over dt. In this one, we set it to 0 to find equilibrium solutions, but now we'll just write dp over dt and go on from there. So what we'll write is, so dp over dt equals 2, I'll just write the initial one, so 0.08 p1 minus p over 1000 minus 15. So we want to solve for p as a function of time, so we want to solve it explicitly. So this equals 2, just to simplify it further, 0.08 over 1000. That's all from here, so I don't want to do that again. So I'll just write this down, 0.08. So it's actually negative 0.08, and then this becomes like that, which is negative 0.08. And then this is going to be p squared minus 1000 p, and then plus 187,500. So that's what that was. And again, make sure to watch my earlier video to see how I simplified it. I basically times 0.08 on this, factor it out, multiply by 1000, divide by 1000, and added a negative sign, just flip it. So we get the p squared as positive, because initially when you multiply p, becomes negative there. And then what I'm going to do now is again recall from that part of the video where the zero functions, or the equilibrium solutions, when you make the 0, we get 750 or 250. In other words, this can be factored out as p minus 750 times p minus 250. So and we'll use those in our partial fraction. So this whole thing equals 2, so this is negative 0.08. Actually, before I write that, I'm going to divide this out right now. So 0.08 divided by 1,000. This equals to, well, 0.08 is just 8 over 100. And then the bottom here is 1,000. And I'm going to simplify this. This is divided by 2, actually divided by 4. This is, if you divide the top by 4, we get 2, and then we can divide this 100 by 4, that's 25. So 8 over 100, same as 2 over 25. Do this again, divide by 2, we get a 12.5. So 12.5 times 1,000, this is going to be, well, 12,500. So just to simplify it further, so now what we finally get is dp over dt equals 2, this negative 0.08 becomes negative 1 over 12,500, like that. And now this one, factored out as explained above, this is going to be p minus 750. Actually, I'll just write 250 in it. So 250 and p minus 750. Just write this in this order. Yeah, so now that we've written this like this, and again, just to reiterate, this part is from my earlier video. You could just factor it out like here, and if you multiply it out, it will get back to this exact same equation. So that's what it equals to. And now what we can do is separate these, just like my separable equations video, by using those method. Again, make sure to watch those. If you haven't, put that in the link below in the description. So we'll divide this out and move the t's on the one side and all the p's on the left side. So we get dp over p minus 250, p minus 750. And then this equals 2, move the dt on this side. So 1 over 12,500 dt. Let's write dt like this. So we get this formula like this. So on the t's on one side, the p's on the other, and then we could take the integral of both sides. But this one here, notice this, we can't solve this too easily like this, but we can, well, separate this using partial fractions. So recall partial fractions. And again, yeah, so that's what this example asked. Partial fractions are used in a computer algebra system. We'll just use partial fractions. So recall from my earlier video on, I'll put a link as well in the description below. These factors, we can write these as, so 1 over p minus 250, p minus 750. This equals to a constant a, times it by p minus 250, which is the first factor, plus a constant b, and then this is p minus 750. So the idea is you separate these into partial fractions. So this full fraction is separated into these partial fractions based on these two factors like that. Now we multiply both sides by p minus 250 times p minus 750. So then this cancels, we're left with 1, and this part cancels, we're left with p minus 750. This one cancels, we're left with p minus 250. So what we get is 1 equals 2, a, and again this cancels, so we get the other one, 750 plus b, p minus 250. The 750 cancels. And then simplify these, or just expand these out, so we get right here a p minus 750a plus b p minus 250b. Now what I'll do is factor out the p's, so we get this a plus b, and we take out the p. So this ap plus bp, same thing as a plus b times p. Now this other part we're going to get a plus, and then what I'll do is separate these together. So this negative 750a minus 250b. The reason we're doing this is because what this is saying is, again, recall on partial fractions. This is a 1 here, and there's no p value, so this 1 has to equal this whole thing, because these are just constants. 1 is just a constant, that's just a constant. And then this also, you could write this as 0 times p. So 0 has to equal to a plus b, because there's no p on the left side. So that means 0 equals to a plus p, and we can write this as, move the b on the other side, a equals to negative b. So that's what we have, and then this part here has to equal to 1. So we'll write 1 equals to 750a minus 250b. And what I'll do now is put in this negative b inside this a. Just plug that in. We get negative 750 times negative b minus 250b. And now what I'll do is factor out this b, so we get b, and then this becomes positive. Let's put a positive, so negative and negative becomes positive. So factor out the b, we get b 750 minus 250. So this means, and this equals to 1 on the left side. So this means 1 equals 2 b times 750 minus 250 is just 500. So in other words, b equals 2, 1 over 500. Let's divide that out. And then a is equal to negative b, which equals to negative 1 over 500. Like that. So there is our factors like that. So what that means is, well, this just equals 2. A is negative 1 over 500 over p minus 250 plus positive 1 over 500 over p minus 750, like that. So that's what this whole thing equals to in the integral, or in other words, the integrand equals to that. We could simplify it, and we could easily take the integral of these two partial fractions. So what we get now is integral of negative 1 over 500, that's the a, p minus 250, and then minus, actually no, plus 1 over 500, and now we have a p minus 750, like that. Put in bracket dp, and then on the right side this is 1 over, negative 1 over 250, 12,500 dt. This is just dt over that. And yeah, just include the integral sign like that. And now what we'll do is simplify this further by taking out this negative 1 over 500. And also this will get rid of that negative as well. So in other words, what we could do is multiply both sides by 500. So I'll write, just times it by 500 on both sides. So when we do that, let's put a separation. So when we multiply by 500 on both sides, what we get is by negative 500 actually. Yeah, so that's a bit confusing. I'll just factor out negative 1 over 500. In other words, when we factor this out, just to make it a bit more clear, so negative 500, this becomes positive 1 over p minus 250. Put a bracket, and this becomes, well, this is gone, but that's a negative now, 1 over p minus 750, and then dp, and then this equals to, well, this is just the same thing, negative 1 over 500 dt, and now we'll multiply by the negative 500 onto both sides, and just basically move this onto this side. What we end up getting is 1 over p minus 250 minus 1 over p minus 750, like that. dp equals 2, and then this is going to be the negatives cancel, so we'll just put a negative 500 on this side because we're moving it over, and then this is negative 500. So this just cancels like that, and then we could divide this out. This is, well, the zeros cancel. Now we're left with 125, 5 over 125. Well, 5 goes into 120 times, and it goes into 25 5 times. So that's just 25, 20 plus 5. So what that means is this equals to integral of 1 over 25 t. So this is just simplified further, like that. And that's what this part equals to. So what this means now is, well, so I'll write this on this side here, 1 over 25 dt. Yeah, so what this means now is we could just integrate this all. Let's move it over there so I could write this on one line. And we can integrate this 1 over p minus 250. Again, recall from earlier videos on logarithmics, integrals. This is, the integral of this is just ln of absolute value of this inside function, p minus 250, like that, absolute value. And then this one we're going to subtract, same thing, p minus 750. And then we're going to add a constant of integration, we'll call that c1. And then on the right side we have this 1 over 25 is constant, dt becomes t, so let's write this as t over 25 and add a constant of integration c2. And also recall my logarithmic properties video, put that link below. This one you could simplify this, combine this into one logarithmic function by whenever you have subtraction, that means you're dividing. So that means ln absolute value p minus 250 divided by p minus 750 absolute value, and I'm going to combine this, the constants, move this on the other side and combine it, so this t over 25. I'll make this a bit over here, and because I'm going to take both sides to the power b, and now we have plus, I'll call this c, where c is just c2 minus c1. Let's move it over, and that's just a constant. So subtraction of constants is still a constant, like this neater. So we have that, and now what we'll do is simplify this further, take the power of e, and put e as a base on both sides, so we're not changing anything. And now we're doing this so that e and ln cancels, as my usual videos on separable equations and deriving the explicit solution for the logistic equation. So this one's a bit more complicated, just more tedious, but same principles. So this e ln cancels, so what we have is p minus 250 over p minus 750, and don't forget the absolute value sign. This equals 2. This one, whenever you have addition on the powers, you can, this is the same thing as multiplication. So this is e to the c times, I'll move that in the front, e to the t over 25. And now what this equals to, we could remove these absolute value signs, p minus 250, by stating the right side is plus or minus. So plus or minus, because the inside can be plus or minus, but it's always going to be positive when you do the absolute value sign. E to the c, e to the t over 25, which equals 2, and I'll combine this plus or minus e to the c as k e to the t over 25, where k is just equal to plus or minus e to the c, which is just a constant. It could be plus or minus e to the c, whatever c is a constant, e to the power of it is a constant, and you add a plus or minus, it's all just a constant. So would we have this, and we could simplify this further by moving this on the other side, or on this side, like that. So we have p minus 250, I'll write this 5 meter, equals to p minus 750 times it by, write this 5 meter, k e t over 25. And now just expand this, multiply that inside, so what we get is equals to p k e t over 25 minus 750 k e t over 25. And now what we'll do is we can move this on the other side. This is just p minus 250. So we can move this on this side and factor out the p. In other words, we'll have p, this one is a 1 in front, minus k e t over, write this neater, t over 25, and then move this p on the other side. I mean this negative 250, so we get equals to positive 250 minus 750 k e t over 25. Divide these out, and what we get is finally p of t is equal to 250 minus 750 k e negative t over 25 over 1 minus k e t over 25, like that. Let's write this a bit neater. E t over 25. Yeah, here I just wrote that a bit neater again. So that is what we have. That's our answer for a generic constant k. Yeah, so that is our solution explicitly, and again, let's scroll all the way up to see the question, and it says, so solve this explicitly either by using partial fractions, as we used, or a computer algebra system. That could have been easier, but this is just more fun. Anyways, so now it says use the initial populations 200 and 300, and then graph solutions and compare with your sketches in part D. So let's do that. So initial population 200, let's do that. So for initial population P0 equals to P at time is equal to 0 equals to 200, what we have, and the idea is to solve for K, and then we can have a solution for that specific initial population. So when we have that, we get 200 equals to 250 minus 750 times KE, and then e to the 0 is over 25, that's a 0. That's just 1. So e to the 0, recall, just equals to 1. Anything power of 0 is just 1. Except if you have 0 to 0, that's something else. You can see one of my earlier videos on that conundrum as well. So anyways, so we have the bottom now is a 1 minus K E 0. So that just goes to 1. So what we get is this 1 over K, we can move this over on the other side, so we get 200 times 1 over K equals to 250 minus 750K. And then this part right here, that's just equals to, put on the left side, 200 minus 200K, like that. So we put it like that, let's write this neater. 200K equals 2, and then what we'll do is this move the K's, move this onto this side, and then we'll factor out the K so that we have a positive, and then move the 200 onto here by subtracting. So what we get is finally this K, actually factor out the 750, just put that here. So K we factored out, positive 750 minus 200 equals to, well, 200 and 250, write this 50 minus 200. So what this all equals to now is this K equals 2. This becomes, this is just 550 equals to, actually put it all together. So this is 550, and this part here is equal to 50. So what we get, and move this over on the other side, K equals to 50 over 550. And then cancel the zeros like that. 5 goes into 55, well, 11 times. So this equals to 1 over 11. So K is 1 over 11 for initial population of 200. And we'll put this all together soon. So now let's look at the second part. For PO is equal to, well, again, P of 0 equals to 300. Only difference now is this is a 300. So what we get is 300 equals to this 250 minus 750K. And then that's just 1, and then 1 minus K, e to the 0 is just 1. So 1 minus K. Move this over, multiplied, we get 300 minus 300K equals to 250 minus 750K. Move this on the other side again. Move this here, combine a 750. We're going to be, so negative 300 plus 750, in other words 750 minus 300, because that's positive. When you move it over, that is just, that's 450. Well, actually I'll just write it down so less confusion and easier for you to follow. So move that over, and this 300 on this side. What we get is 750 minus 300 K equals to 250 minus 300. This equals to negative 50. And then on this side, I'll put it on this side, so equals to 750 minus 300, that's just 450K. So what we get is K equals 2, and then divide the 450 out. Negative 50 over 450, the zeros just cancel. 5 goes into 45 9 times, so this equals to negative 1 over 9. Like that. Yeah, so now what we have is our solutions, or the K values, and we can plug those into the solutions. So what we'll write is, so thus, for PO, for the initial population of 200, for PO is 200, also note that K equals 1 over 11 in that case. And now we just plug in our K value. Yeah, so plug that in. Let's just recall the formula we had. So 250 minus 750, KE T over 25, 1 minus KE T over 25. So we get P of T is equal to 250 minus 750 over, and then K, which is 1 over 11, so just divide that out. E T over 25, and now we have this 1 minus 1 over 11 E T over 25, like that. So that's what that was here. But my calculus book simplifies this further, and it does that by, well, multiplying both sides to make this a positive on the E T over 25 and getting rid of these fractions. What it does is multiplies both sides by negative 11. The top and bottom by negative 11. So it does that, bring this in, and also factor out this 250. What we get is, well, when you factor out 250, this goes into it once, this goes into it 3 times. 250 times 3 is 750. And then this negative 11 cancels with this negative 1 over 11. So what we get is this 3, is that we took that 250 out. 3 ET over 25, and now that's gone, so now we put this negative 11. So negative 11, we multiply that inside. And then the bottom becomes, well, negative 11 goes in here, this becomes positive ET over 25, so put that to the left side, T over 25. And then this 1 times negative 11 is just negative 11. So this is our solution. Yeah, so that's our solution for initial population of P is 200, or population of 200. So now let's look at for P of 0 is equal to 300. So when this equals to 300, the only difference now is the K is equal to negative 1 over 9. So similarly, we could plug that in, but if you want to simplify it, we're going to plug in negative 1 over 9. And then, so instead of multiplying by negative 11 over negative 11, we'll multiply by just positive 9 over positive 9, because that's negative there. So what we end up getting is, instead of this, similarly, let's write that similarly, just to save some time and space, we get P of T is equal to 250, and then this is going to be 3. So basically exact same thing, but instead of negative 11, we'll have a positive 9. So this is T over, oops, what's going on there? So 25, and now instead of negative 11, it's a plus 9, like that, over, and then this is going to be ET plus 9. So we just simplify that further. So just to save space, we just do that. The only difference was that this negative 11 becomes positive 9. And also notice here there's a 3, and this was a factor of 3, so we can just take this out, and what we'll end up getting is this 750. So when you 250 times 3 is 750, so equals to 750 times, and then we factored out ET over 25 plus 3 over ET over 25 plus 9. So I'm just simplifying it because my calculus book has it simplified to this formulas, or these formulas. Yeah, and now the next step was to graph that solution. So I've graphed that giant formula 750. This is for for P of 0 is 200. That's our 750 times e to the power of t over 25 plus 3 over e to the power of t over 25 plus 9. So we got this formula right here. I put this in the Google search calculator, as well as graphing 750. You can't put a population, you can't put the variable as p, so y will do. So y is this p. and then also 250. So we had the line like this for this is the orange one is is the 250 population, and let's just change this to that. As you can see, this is 250, and the green here is the population of 300 initially. Actually, no, this is population of 200 initially. This was population of 300. I mistaken that one. Yeah, I got these mixed up. So this was the population of 300. That's because of the 750, and the population of 200 was 250 taken out, and there's a 3, there's a negative 11, etc. So when the population is under 250, notice that it goes down to 0. So you start off at 200, and it goes down to 0 like that. And then when we have the population of greater than 250 at 300, and as you can see, it's going and approaching this red line of 750. The only thing, this line above here, that's just ignore it. That just doesn't. That's not applicable to this solution. That's just basically based on the nature of that solution. You could have something like that. But this is the one we're starting at 200, so that's just an unrealistic part we could ignore. And this is how it looks like. And just another note on this: when you're using Google Search Calculator, sometimes if you were to write a formula to graph it, the x and y coordinates might be really messed up. For example, I'll just copy this one. This is the exact same one as this. But the initial one, as you can see here, and it's 750. You see the coordinates are really too small, and then the x and y. See, this is 2,500, 500, 5,000. So this is all messed up. So you'll have to actually go in and fix it yourself. So zoom in and out like that until you get some sort of reasonable data, especially onto the other side like this. Move it over. You gotta zoom in and out and in. So yeah, basically you would have to fix it up yourself. Sometimes you have to do that. Just I don't know why it messes up really badly. But anyways, once you do that, you should get something like this, and that's how it looks like. So let's get back to here. And here I've copied and pasted that graph. So this is our t. This is at p is equal to 250. This is at, this red line is p equals to 750. These are the equilibrium solutions, and this one just ignore. That's just not a reasonable solution because the initial population is here. So this is a p300. So the green is p0 equals to 200, and then the blue is to 300. It goes to 300 like that. And as you can see, it starts off from here. That is p0 equals to 300, and then it goes up to the 750, levels off like that. But as here, when you start here, it goes down to 0. In other words, this is put an arrow. This is overfishing. So when a initial population is really small, and you're fishing at 15 fish per week, that's overfishing. You're just gonna kill all the fish. It just goes to 0, and they can't repopulate themselves. And now when we compare this with the solution, the graphical estimation solution from the direction field in example 1 part 1, well, as you can see, there's the PO 200, and following the direction field goes to 0. And 300, as you can see, levels off and goes to there. And then it's pretty much exactly what we graphed. And yeah, that's all for today. Graph and compare with sketches, and it looks good. Anyways, that's all for today. If you follow along this very extensive example on finding the explicit solution of this modification of the differential logistic equation, and notice how just by putting this negative 15 makes it much more tedious and complicated to solve explicitly than if you had this removed, because if you saw my earlier video on the logistic equation explicit solution, I solved that much simpler than the one over here. But regardless, it's the same idea, just more tedious. Anyways, hopefully you followed through this very extensive video, but it's a very good refresher on partial fractions and other just algebra and logarithmic differentiation and properties, etc. So it's good to follow through. It's really good mathematics in here. Anyways, that's all for today. If you learned, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.